Hi guys, so let's start with building our machine learning models. In this video, we are going to talk about simple linear regression model. So I'm going to focus a lot on the foundation part so that you get better hang of the concepts. You don't have to worry about the calculation part. I will show you everything in the simplest possible way. But honestly, I don't think it is very complicated. You will enjoy it. It's just that if you are new to calculation and all these kind of things, it may take some time. So go over the video again and again. The most important part is the calculation part. Rest of the information is important, but it's theoretical. So once you get hang of the simple linear regression, you know what we are dealing with. So as I have mentioned in one of the earlier videos, regression is basically used when we are looking to find out a continuous value, continuous variable. And this is used when we have two or more than two variables and we are looking to find out interaction between them, relationship between them. So in simple linear regression, we will have only two variables. One will be dependent and one will be independent. So we need to find out if there is a relation between them. For example, speed and the distance. This is a very common example used in the world of machine learning to explain simple linear regressions. So if we increase the speed, we can cover more distance in a given time. So in 1 hour, if we are driving at the speed of 50 miles or 50 kilometers per hour, and if we increase the speed to 80 miles or 80 kilometers per hour, we are going to cover more distance in 1 hour. That is keeping the time constant. As we are dealing with data, then outliers and missing values will usually impact linear regression. So when you are working on linear regression problems, whether it's simple linear or multivariate, you need to make sure that you are handling your missing values or outliers. A lot of time outliers are simply dropped and missing values are either replaced or dropped depending upon their numbers. If the missing values are very less, it's better to drop those values. But if your data set has high level of missing values, then you will need to find out better ways of handling them before you apply linear regression on them. Relationship could be proportional or inversely proportional, or rather directly proportional or inversely proportional. For example, in case of speed and distance, if we increase the speed, distance will increase. This is directly proportional relationship. But if we have a relationship where if we increase the independent variable, the output, that is our dependent variable, goes down, then the relationship is inversely proportional. So just to show you in terms of graph, this is our positive regression line which is encountered when we have directly proportional relationships. Whereas if there is an inverse proportional relationship, then the line will go down, that is, we will get a negative regression line. So as you can see, as values are increasing on the x-axis, let's say this is our independent variable, values on the y-axis, which is our dependent variable, are going down. So values are inversely proportional to each other. In terms of representation, so this is a common formula which is used for the denotation of simple linear regression. So we have y hat equals to beta 1 x plus beta naught. Beta is basically parameter of x, whereas x is the input variable. So usually we will find out the beta 1 and then we will calculate to find the beta naught. Now I know this is getting confusing. So let's use a different representation which is used for denotation, which is right, absolutely right. It's just that it's different, slightly more, you can say, user friendly. So that representation is this: y equal to mx plus c. This is the formula for simple linear regression, where m is represented by this formula. And don't worry, I will show you exact calculation. I know if you are not used to formulas and calculation, it may get scary, but this is really, really simple. I will just show you in a bit. So The numerator is product of x minus x bar and y minus y bar, and then we need to add them. Denominator is x square of x minus x bar. So we will find out y and x from our data points. Then we will calculate m. And then once we have these values, we will calculate c. So without confusing you more, let me jump into the Excel where I have simplified them, and it will be really easy for you to understand. Don't worry, we will look at the implementation in R, but in R it's a one-liner code. You won't get the backend part. So it's important to understand the concept. For that, I have used Excel to show you the exact calculation. Okay. So I have created this chart, this entire calculation. At this moment, just by looking at everything, it might be overwhelming. So don't worry, I will explain everything. We have two variables here. Y variable is our y-axis, which is, let's say, this is our dependent variable. And x is independent variable. All right. And this is the chart. So for now, just look at this chart. Ignore everything on the screen. So we have these values starting from 0 to 12 on the x-axis and 0 to 45 on the y-axis. So these are the points, individual data points. So when x is 1, y is 15. When x is 2, y is 12. Similarly, when x is 3, y is 18. And all of this is coming from here. So you can see when x is 3, y is 18. Then when x is 4, y is 24, and so on. This red line is the linear line which I have inserted into the graph using the Excel functionality. So this is the linear line. But right now, that is not our concern. We first need to find out the intersection. So for that, this orange line here, this represents the mean of x. And this yellow line represents the mean of y. And this is our intersection point. Let's go back to our data. So this x, if you see, mean of x is 5.5 and mean of y is 26.6. So this line here, the orange one, is around 5.5, and this line here, this is around 26.6. I have manually drawn it, so I agree that this line is slightly past 5 and this line is probably closer to 26. But apart from that, they are representing overall reality. So this value is 5.5 and this is 26.6. And if you remember, this was our original formula, y equal to mx plus c, where m was represented by this value. So here if you see, we have x minus x bar, y minus y bar, and square of x minus x bar. So first we need to find out these values. X mean the data points at the x-axis and x bar mean mean of x. Similarly for y minus y bar, y mean the individual data point and y bar mean the mean of y. So what we are going to do? We are going to calculate x minus x bar first. So here I have simply taken x minus x bar. So 1 minus 5.5 is 4.5, 2 minus 5.5 is 3.5, 3 minus 5.5 is 2.5, and so on for all the values. So, but formula remains same, x minus x bar. X bar is the mean. So we are taking individual values from here and then subtracting it from its mean. Similarly, we are doing exactly same thing for y bar. So first value is 15. We are subtracting it from the mean. Similarly for next value, then third value, everything. Take y minus y bar. So we have values for x minus x bar and y minus y bar. Alright, so if you see, this is our numerator, x minus x bar, y minus y bar. Then we need to find out the denominator, which is x minus x bar square. So we already have this x minus x bar, we just need to square it. So 20.25 is the square of minus 4.5. 12.25 is the square of minus 3.5. This denominator is nothing else than square of this value, this column. So all the individual elements have been squared. Okay. So to solve the numerator, which is x minus x bar multiplied by y minus y bar, we have multiplied these two values. So this column represents x minus x bar. And if when we add everything here, that is summation. So if you see, we have the summation sign here. So we need to find individual calculation of x minus x bar multiplied by y minus y bar and then add everything up. So that is 218. So that is going to be our numerator. For x minus x bar square, we are going to do same thing. We are going to find the square of all these numbers, put them here and add them. So it becomes 82.5. When we solve this, that is 218 divided by 82.5, we get 2.642. So now we have y. Y is y mean. Okay. So y equal to mx plus c means y equal to 26.6 and x is 5.5. So we are going to use these two here. Y equal to 26.6, x equal to 5.5. We have calculated m from here. So we will put these three values in this equation, solve it like this, and then we get the value of c, which is 12.069. So that's how we solve the formula for linear regression. But question is, this is used in predictive modeling. How does it help? It helps because initially when you come up with this chart, we don't know the values of m, we don't know the value of c. So we use this formula to calculate the value of all the variables in this equation. And then we use them for prediction of y. Remember, y is our dependent variable. So here we have points up to 31. Okay. And x is 10. X is till 10. But in real life, when you use predictive modeling, you first train the data, which means you will use this data set for training, and then you will feed the unseen data. That is, let's say you will feed 100 into this model, and you want your machine learning model, in this case simple linear regression model, to determine what will be the value of y if the value of x is 100. In that case, in this formula, you will replace the value of x by 100 and replace the value of c by 12.069 and then find out the value of y. So the equation will be y equals to 2.642 multiplied by 100 plus 12.069. Let me increase the font size. So this will be your predictive model. And this is simple linear regression in a nutshell. Okay? I hope it's helping. So you first have an initial equation. You solve that initial equation to get the values of all the input items, and then for the given value of x, you try to find out the value of y. And then you draw a line of best fit. So this line, if you see, there's a difference between the line and the individual data points. This data point where the value of y is 12 and value of this point here is somewhere, let's say 18. So there's a gap between line plotted by our model and the actual value of y, which is 12 in this case. This difference is called residual error. The overall approach is to minimize this error. Our model should come up with a line which is closest to all these points. So in this case, this point here, where y is close to 26, if you look at our red line, linear regression line, this is very close to this actual point. So this is kind of, you can say, ideal world linear regression model where this difference, this residual error is least. So that's how linear regression model works. If you have any question on this calculation part or anything in general, please leave your comment. But the overall in linear regression, this is what you do. You try to find out the value of y for a given x. In order to do that, you first need to solve the equation for linear regression. Let's jump back into our slide and cover some more important topics. So this is the same thing. So for if value of x is 100 or 1000 or 10,000, whatever value you can come up for x, you will use this equation to find out the value of y. And then I have mentioned here the terms like beta because again these are commonly used in the industry and somebody is using formula with the beta naught. You need to remember this same formula mx plus c. That's it. They are talking about parameter which is m in this case. So beta 1 is called slope parameter and beta naught is called intercept parameter. So beta 1 is your m and beta naught is your c. These are also referred as secret of nature because in reality we don't calculate parameters, we estimate them. So this is in the good old world of statistical analysis. That's how it's called. So if somebody is asking you what is secret of nature in a linear regression, you know they are talking about beta parameters, which is also called as regression coefficient. In simple linear regression, the method which is used is called least square method. So basically, to calculate the difference between the linear regression line, the red line which we saw, and the individual data points, the method we use is called least square method. And there is another way of solving this equation, that is by using the chart. You'll find beta naught when the y-intercept is equals to 0. And then you'll find the beta 1, which is whenever you change x by 1 unit, you will calculate the change in y using the plot. In this chart, we are saying that when you change x by 1 unit, you observe a change in y by 2 units. So in this case, we will divide them. So b1 will be 2 divided by 1, which is 2. It could be anything. So let's say when you change x by 1 unit, you observe change in y by 20 units or 40 units. So you will use that for calculation. But the easier and the better option is mx plus c using the data points you have. But again, all of this is happening in statistical world. In machine learning, we are not going to manually calculate these things. We will simply use RStudio for R or Python or whatever language you are using, and that will do the job for us. This is the negative regression line which I have shown you earlier. In terms of hypothesis, this is how you are going to represent your null hypothesis. So which means that H naught or HO here simply means null hypothesis. But in machine learning problems, in machine learning projects, you're not going to use this. You will simply say H naught. There is no interaction between given variable. If we have speed and distance, you will mention that there is no interaction between speed and distance. And as I have mentioned, residual value is basically the difference between the actual values of y and the predicted values of y. And predicted value simply means our red line. And in terms of mentioning key concepts, you need to remember homoscedasticity and heteroscedasticity. So when there is similar variance in different samples from same population, we call it homoscedasticity. And when there is no similarity or differences, we talk about heteroscedasticity. And these are important key concepts, key terms which are used in interviews. So that's why I have mentioned it here. So if you are preparing for interviews, make sure to remember them. And if we were to include more variables in the mix, so instead of, let's say, just speed and distance, we also include something like horsepower of the car, displacement of the car, or whatever parameters a car have, then we are looking at multiple linear regression. So overall mechanics, overall concepts of linear regression will remain same. The calculation part will remain same. It's just that the equation will expand to include more variables. So you can see that we have beta 1 x plus beta naught plus beta 2 x2 and so on. So overall equation will remain same. It's just that we will include more variables into the equation. But as far as functionality is concerned, the concept is concerned, it will remain same. So in the next lecture, we will go through their implementation in R. Thank you.